Hello, everyone. My name is Kamzolov Dmitry. I'm a researcher in Moscow Institute of Physics and Technology. And this is our joint work with Pavel Durechensky, Alexander Lukashevich, Sumin Lee, Eric Ardentlich, Cesar Uribe, and Alexander Gasnikov. And this is work about hyperfast second-order local solvers for efficient statistically preconditioned distributed optimizations. Next, I will describe in more details what every word means in this. So the plan, first I will speak about Highorder methods. Next I will speak about hyperfast second-order methods and what is it. And the last part will be about distributed version of this method, statistical preconditioned distributed method. So first, let's start with the Highorder convex problems. Here we have we assume that we have function f of x. It's convex functions with Lipschitz path derivative. So and with this constant LP. So we assume that we have functions with many derivatives, like the order of p, and all of them are smooth and continuous. So this is the definition of Lipschitz derivative. It's similar to if, for example, if p is 1, so it's naturally the gradients and the smoothness of function in terms of gradients. And like for gradient descent or cubic Newton method, we can create Taylor approximations of pth order where our function will have a lot of derivatives. And from this Taylor approximation and this Lipschitz derivative inequality, we can get next corollary. That's the Taylor approximation is rather close to our function. So this is the main inequality, and similar to the gradient descent, we want to move this part to like omega part to the right, and make the methods find arg minimum of such model, and this will be our tensor method. But the problem is that these derivatives and this model can be non-convex. So naturally, the subproblem will be much harder than the original problem, and this is bad. But Yuri Nesterov in 2018 proved that if we multiply this norm by p or p plus 1, the function will be convex, and the tensor method will works good, and so we can use it. And basically, like if this part is convex, so it's okay. And for such HP that's greater than LP, the subproblem is convex and hence implementable. We can solve this problem somehow by other methods. So the convergence of such scheme is rather good. It's n in power of p. Naturally, for gradient descent, p is equal to 1, so it's only n. For cubic descent, cubic Newton method, it's p equal to 2, and our focus will be p equal to 3. So it will be n power of 3. Next, in the same paper, Nesterov described and proposed accelerated tensor methods. It's look like this. It's use the same step here and some acceleration step with gradients here, like Nesterov acceleration, and this is the model of the gradients. Convergence on such methods is this method is faster. It's p plus 1. So for first order methods, it will be n to power of 2. For the second order methods, it will be n power of 3. Okay, next move to optimal tensor methods is the work by Gasnikov and other colleagues. 2019. Here it's a little bit harder to understand. This like YK+1, it's the same step as the previous in previous methods, but we have some additional line search here. It's two inequalities, and so firstly we fixed some lambda. Next we calculate small a. Next we calculate big A, point xk tilde from small k and previous points, and after that we calculate tensor step, and we try to after this all calculations we can check the inequalities. If it's inequalities are satisfied, we continue with step 5. If not, we change lambda with some algorithms like some line search procedure, and normally it's it proves that it's this line search is not very big. It's rather good, and in terms of practice, I can say that this line search actually rather good, because normally it's not greater than 4 or 5 times per iteration, but many iterations are satisfied from the first line search. First lambda is good for this all procedure. So, but why we need this line search and all these tricks to get this optimal convergence. So, for example, for second order methods, it will be 7 divided by 2, and for third order methods, it will be 5. But and the previous methods have n power 4, so it's a great and better convergence. Next, we move to inexact solutions and to how to solve this problem better. So if we assume that we have an exact solution of such problem, so this is the definition, and so that the norm of the gradient of submodel should be smaller than some divisor of the norm of the true function, and this leads us to such methods. It's our methods that we prove that with such type of steps, methods converge and have the same complexity. And this is a special procedure called Bregman distance gradient methods, proposed by Nesterov. That's by this procedure we can solve our subproblem efficiently. Why? So here we can see that this is normally our subproblem for p equal to 3. So it's the first the gradient, the second derivative, and the third derivative. And we use Bregman distance, so we prove it can be proved that for such function, scaling function rho, we can use Bregman distance gradient methods to solve this subproblem, and it will converge very fast. And normally, like it's linear and with the constants of convexity, relative convexity, and the relative strongly relative smoothness and relative strongly convexity, phi for relatively to rho is some constants like 4 or 1, and so the condition number is also some constant, and it's very good, and we converge very fast. But we need to solve on every step Bregman distance gradient method this subproblem. And what is the main cool part? That G, it's here we can see it's inexact third derivatives. So this first is okay, second is okay, but third derivative we don't want to compute exactly, and because of we don't need to compute the full third derivative. We only need not to know third derivative gradient, like the gradient of this function. So this leads us to some additional procedure. Like here, we can approximate it by sum of the gradients, or we can compute it by outer gradient by computing like if f is good, we can compute it by outer grad, like in PyTorch or TensorFlow, and it will be as hard as compute like 8 gradients. So first you can assume that this part is very hard, but actually it's not very hard, and it's like 8 computation of gradients. And here we can we will have this subproblem is normally contains some linear part, this part, and this part. So it's quadratic optimization with some regularization, and it can be solved by like some first order methods or special procedure with inverting this matrix. And also I should mention that this subproblem is equally hard as subproblem of third cubic Newton method. So basically all of these methods for p equal to 3 is as hard as methods for p equal to 2. So we by this all these tricks we can lead to these methods. Here it's p, every p is equal to 3, and we converge fast. N will be equal to 5, n to power of 5 the convergence, but the implementation could this is a convergence theorem, so we can here we can see that n here it's power of 5, and normally for second order methods it's n power of 3 or 7 divided by 2, and so this is very fast, but also, as I say, not very hard to compute. And what is next? We want to use it for distributed optimization. So let's move to the empirical risk minimization problem. Here is the empirical risk minimization problem, where we assume that it's convex problems, and we assume that also the function is f is strongly convex with respect to sigma f, and this is the condition number of such function. So it's next. Let's move on to the distributed configuration, distributed setup. We assume that we have m computing units, and the total number of data divided by these m computing units. We also think that the central we have the central node, and all other nodes communicate directly with the central node. So, and central node also has some data, and we so here it's a distributed empirical risk minimization problem, where we divide all our functions into m parts, and also we assume that f1 of x it's a central node. And so what is the main idea of our next methods? We assume that this we assume that the central part, this is like central, this is reference function, similar to Dane and Spag, and this function is, we assume that it's similar to statistically similar to the whole f of x. So here we can see in equation 5 that we assume that the Hessian of all function fx is similar to the Hessian of f1 fix, so it's only central node part. And under this statistical similarity, we will create this function. So it can be proved that f of x is LF sigma relatively smooth and relatively strongly convex. So like this equation, inequalities can be written and with these constants. And this means that we can use the Bregman proximal method with this LF, and also like we can assume all of this strongly convexity, and this leads us to our method. So we normally, this part, it's some central node part. We compute Bregman distance, compute some additional parts to accelerate this method, because we use like this method, but accelerated variant of Bregman proximal method. So this is parts are dedicated to the accelerations. YT t plus 1, it's also some computed in central node, and this is will be our point. We send it to workers. Next, at every worker, they compute the gradients of their functions and send it to central node. And in central node, we aggregate this all gradients, get the full gradients grid of our function, and create some such problem where V it's contains the gradient, and Bregman distance dedicated to phi. Here's the Bregman distance. So normally this problem, it is some. So here we will have some functions f, but only contains phi. So what does it mean? It means that problem VT, it's some easy problem in terms of it contains only functions f and l that are on central node, like this one. This functions and data only on central node. So these functions contains only central node information, and the information from workers can in gradient of f. So this subproblem is much easier than and much smaller data we need to solve this subproblem. And this subproblem 11 and 12 we will solve by Hyperfast method. So this leads us to our method. The outer procedure is in exact part. So we need to solve this inexactly, and naturally we compute the full gradient of f on the central node on the workers, and that's why it's much faster than compute like yeah. So we use our distributed framework here, and here we use the Hyperfast part, and this because it's for small problem. We don't need to compute all gradients and all Hessians here. We compute only Hessians for a small number of points that are in our central node. This leads us to the next convergence theorem. So it's from this theorem we can get like this is our main speed parameter, and here we can see that's what does it mean at. Normally it's the power of t if g is small, and like this one is linear convergence with such number. This all of this leads us to like this is easier formulas. We have the best communication complexity here because it's like the best known communication complexity for such architecture, and it's as a Spark, and it's accelerated communication complexity. And that complexity with Hyperfast, this formula, also we can here see this power of 5, and normally it should be smaller, like 1 power of 5, yeah. And for if we don't use Hyperfast, the number 5 will be like 3 or 4 or something like this. So next, move to the main part to show why is this good and why does it works. It's experiments. So we normally use two data sets, RCV1 and in-house data from our colleagues from Yahoo. And this one is rather small, but not very small, as I say. This is a dimension. This is the number of points, number of data sets. And for in-house data, this is a dimension. So it's 3 million dimension and 700 million data points. So this is actually a very big data set. And surprisingly, for all these data sets, Hyperfast method works. So this is experiments for CV1. Here we can see yellow and this one, it's Dane, and blue and red, it's Spark. So both Spark plus SDCA and Spark plus Hyperfast is faster than Dane, but also we can see that Spark plus Hyperfast is better than Spark plus SDCA. So this one is method from previous papers, and this one is method from our paper. So we can see that it reached much more precise solution, but by 70 communication rounds. And next slide, we can see also that in wall clock time, so our performance will be better. This is on first iteration in exact Spark plus SDCA is faster. So if you don't need to solve this problem very precisely, you can use in exact Spark plus SDCA. But if you want more precise solution, you should use in exact Spark plus Hyperfast, because we can see here that it's faster and better solution even in terms of time. And also I should mention that in practice we find some like some, I don't know how to say, tricks, features that Hyperfast is becomes much faster closer if it closer to solution. So in first iterations, it's really not very fast, as you can see. And in terms of time, it takes a lot of line search on the first iterations, but on the last iterations, it's like the line search contains four steps only, like in 10 iterations, or like 12 iterations, and other 9 iterations from this 10 iteration cycle. Every iteration is one line search, so it's much faster than it can be assumed. And next, we move to in-house data. This is a really big data set, and this is experiments for inexact Spark. We see in plus SDCA, we see Hyperfast. So in this, like green one, it's naturally inexact Spark plus SDCA. So one variant of an exact hyperfast is slower. It's because the constant L is rather big and not very good chosen. But if we tune this constant, we will converge better. And so blue one, and it's the variant of such parameters. Also, I should mention that the very inner subproblem we subsolve with Adam subsolver, and this number is the number of data on the central node. So also it's rather interesting that you can see from the blue one and the purple one that in the purple variant we have less data points on the central node, but we actually converge faster because this one is of D, and also it's in communication source, even not in time, but also in time because the inner subproblem will be easier, we will converge much faster for such variant. Also, this is like in-house data. It's 3 million dimension. It's for me. I think that it will be impossible to compute third-order methods for 3 million dimensions. But it's possible, and it's outperform first-order methods and other methods. So this is the last part of my talk. Thank you very much. Thank you for your attention. Any questions?
Please, questions. Very nice talk. Thank you, Dima. And very big work. It's for about 1 year, the duration of this work.
Yeah.
It's a lot of experiments, a lot of details. I would like to indicate that this is really a very, very accurate work with too many details. Okay, maybe questions. Well,
maybe I should mention one point. It's surprisingly for me, as I have a little bit time, that I hope it's like we was lucky that hyperfast is actually one of the fastest methods in between all, as I know, hard methods. So like between this one and this one, like all methods that hard methods I present, actually it's rather fast, and actually the line search are rather fast. And I think it was rather lucky for us that we chose even exactly this method to make these experiments, and it's actually works even on such big dimension. Oh, okay, I think
okay, thank you very much, Dima. Thank you very much. This is a very important comment. Yes, I agree. Okay, thank you.